We've learned that there are two ways to produce the Doppler effect. Here's a car with a horn, and it's blaring its horn. And here's a person who is listening to the horn. Which is the source of waves, and which is the observer? Well, the car is the source because it's producing the waves. It's producing the sound. And the person is the observer because she is hearing the sound. So the Doppler effect is when the frequency that's emitted is different from what the person hears. She hears a higher frequency, or maybe she hears a lower frequency. And one way to produce this effect is the source is moving toward or away from the person. But the other way to produce the effect is to have the person traveling toward or away from the source. This velocity we call the velocity of the source, and this velocity we call the velocity of the observer. Because they are both relevant, they both appear in the equation for the Doppler effect. So what is this equation? Well, it's important. We're going to use it quite a bit. F prime is the frequency that the observer hears. It's the shifted frequency. F is the regular old normal frequency emitted by the source. It's the frequency that the source would hear. And it's also the frequency that the observer would hear if there were no relative motion. Okay, c is the speed of sound waves, how fast they go in the medium, and it's always the same for a single medium. And like we said, VO is the observer speed, VS is the source speed. Note the units, and note the sign. VO and VS can be positive or negative. The rules for determining those signs are shown below. And the basic idea here, approach means positive velocity, receding away means negative velocity. So let's practice that real quick. Let's say the person is moving to the right and the car is moving to the left. What are the signs of these velocities? The answer is the source has a negative velocity because the source is moving away from the person. This is going away from the person. And the observer would also have a negative velocity because she's moving away from the car. She's receding away from the car. Okay, what if we had this scenario? The car is moving to the right, and the observer is moving to the right. What are the signs of these velocities? The answer is the source has a positive velocity because it's approaching the person. It's going toward the person. But the person has a negative velocity because she's receding away from the car. She's trying to move away from the car, so that's a negative velocity. So there's a lot of scenarios we could construct. We could have both positive velocities like this. We could have both negative velocities like this. But then we could also have one positive, that's approaching, and the other a negative. The car is negative because it's receding away from the person. Let's look at an example. And first I want to point out, it says for all of these problems the speed of sound is 330 meters per second. Let's try number 2. A person is standing on the sidewalk watching a car drive toward her at 28 meters per second. The car blares its horn, emitting sound waves with a frequency of 680 hertz. Find the frequency heard by the person. So she's standing. That implies that this person is not moving. So the observer speed is 0. She is the observer because she hears the waves. The car is driving. The car is the source because it emits the waves. And so the source speed is 28, and it's going toward her. That's approach. That makes it positive. It emits a frequency of 680. That's the emitted frequency. That's just regular old F. We have to find the observed frequency, F prime. The equation is F prime equals F, the emitted frequency, times a fraction. So the emitted frequency, what's that? It's the 680. In the numerator of our fraction, we add two things. In the denominator, we do a subtraction. Okay, in the numerator, we take the speed of sound, that's 330, and we add the speed of the observer, which is 0. Down below, we take the speed of sound. The waves travel at 330 meters per second, and whoops, we subtract the speed of the source. So we're subtracting a positive 28. When you do this in the calculator, what do you get? 743.0. Note we should have 4 sig figs if we follow our sig fig rule, because all the givens have 4 sig figs. So 743.0. That's a frequency, so the unit is hertz. And we could prove that the unit is hertz if we look at units inside, but we're not going to worry about that now. Next, determine the wavelength observed by the person. The wavelength observed by the person, that would be like lambda prime. Well, we know the frequency observed by the person, so we can find the wavelength observed. I'm taking the wave equation and applying it to this scenario. So the speed is 330 as before. The frequency we just found, 743.0, blah, 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 keep those extra digits, and you solve for lambda prime by dividing. I divide 743 by both sides, and I get 0.4441. Lambda prime is 0.4441 meters. Okay. Once the car passes and is receding away at 28 meters per second, now what's the new frequency the person observes? So we're finding f prime again, but now the car is receding at 28, which means the source speed is negative 28 meters per second. So the calculation is the exact same. I'm not going to write it out again. I just want to point out, instead of subtracting a positive, now we have to subtract a negative. And those are going to combine to make 330 plus 28. So the denominator is now going to be, second enter, I'm going to come over here, and I'm going to end up adding, because it's a negative velocity, I'm subtracting a negative, which means I'm adding the 28. 626.8. So that's going to be our answer. And just like before, we can use C equals F lambda, apply it to the observed frequencies to find this.